Good afternoon, everyone. I welcome all the participants to this online faculty development program on optimization technique for engineering application from 11th March 2024 to 22nd March 2024. So all the sessions will be conducted in Google Meet, and the link for all the session is same, whatever I have said with you. And I have also shared the material link with you. You can go to WhatsApp description and you can find all the video links and material links and Google Meet link there. And Google Meet link is same for all the session. So this FDP is conducted by E&ICT Academy of NIT Warangal and Department of CSE, National Institute of Technology, NIT Warangal. So the coordinator of this program is Professor Manjuwala BC Madam and myself. We both are working in the same department of computer science, and we are the coordinator of this faculty development program. So as I have said, the program schedule, you can see it is a 10 days program, and every day we have 4-hour session. 3 to 5 we have one session, and 5 to 7 we have another session. So we have 4 hours and 2 sessions of 2 hours each. And also we have requested various faculty members outside NIT Warangal to deliver the lectures in this faculty development program. They are Professor Prakash Kotecha, Associate Professor, Department of Chemical Engineering, IIT Guwahati, Professor Akhtar Khan, Assistant Professor, Department of Mechanical Engineering, IIIT DM Kurnool, and Professor Saroj Patel, Professor in the Department of Mechanical Engineering, NIT Roorkela, and Professor Sarat Naik, Software Computing Lab, Yonsei University, Seoul, South Korea, and Professor Sivram Panigrahi, Assistant Professor, Department of CSE, NIT Roorkela, and Professor Love Kumar, Assistant Professor, Department of CSE, NIT Kurukshetra. So we have total of 20 sessions. Some of the sessions also contain hands-on session, or some sessions are also theory and practice in the same session. Like you can see in the Tuesday timetable, we have MATLAB optimization toolbox. That if you have installed MATLAB in your system, then you can also do hands-on with the speaker. And also we'll see some of the hands-on in other type of optimization algorithm throughout this faculty development program. So it is a 2-week program. So we don't have any class on weekend, that is Saturday and Sunday. So from today onwards, we'll go for 5 days. Then again, we'll start on next Monday and we'll continue for another 5 days. So Saturday, Sunday, we don't have any classes. And if any specific software is required, apart from MATLAB, if it is given by the speakers, then I'll share with you in WhatsApp as well as in email, so that you should be ready with that particular setup, which will help you to do the hands-on session. And I'll share all the videos in view mode, so that you can see if you have missed the class due to internet connectivity issues. And I'll share the material, but material is purely depends on the speaker. If the speaker is willing to share the material, then I'll share the material with you. Otherwise, you can see the recorded session, and if you have missed it, you can go through it. And on the last day, that is 22nd March 2024, we'll complete our session by 7:05. Then around 7:30, we'll conduct a MCQ test. So you have 15 MCQ questions. Each question carries 1 mark. There is no negative mark. And you can write the exam before the midnight. So we are very flexible in that, but you have to attend the exam before midnight. And your attendance and these feedback as well as appearing the exam is mandatory as per E&ICT norm. So this is the information just I want to share with you before we start the first session. Let us start the first session. So in this session, I'll tell you about non-traditional optimization methods. And in the second session, we'll see simulated annealing algorithm and end colony optimization by Professor Manjuvala BC Madam. So let us start this session. So as the name suggests, non-traditional optimization methods. So non-traditional means I want to mean that we are heading towards the modern optimization methods, because optimization method is not completely new. It is there from long back, but the way it is applied in various applications or the different variations of the previously developed algorithm or hybridization makes optimization method a popular platform to apply in various domains. It is not restricted to the field of computer science or field of mathematics, but there are quite good researchers who are applying non-traditional optimization methods in various domains like civil engineering, metallurgy, mechanical and electrical and other domains also. So you can also look into different type of optimization methods, which is going to be covered in this FDP. And if you apply such optimization algorithm or recently developed algorithms to your respective field, then I can say it is more fruitful to you. So what we are going to discuss here, I'll tell you about why we are heading towards non-traditional optimization method, why traditional optimization methods are uh, not efficient. Once we discuss about that and we'll see the history of this evolutionary computing, then I'll more focus on one of the very popular algorithm that is called a genetic algorithm. And throughout my presentation, I'll show you some of the mathematical applications of genetic algorithm, where you will see how to model a particular application or how to solve a scientific or engineering application through genetic algorithm. And followed by, I'll show you some of the references where you can look into if you are interested to apply genetic algorithm or variants of the genetic algorithm in your respective research domain. Now, if you go for scientific or engineering applications, as you are a faculty member or a student in science or engineering field, we know our problems are very complex. We start with a very simple problem, but if you go for generalization of a particular problem, such problems are very complex. Or we can call that problem are large scale problems. So if you apply non-traditional, if you apply traditional optimization algorithm, it is difficult to solve those problems. What I mean to say, with the traditional optimization solutions, you can apply linear programming, you can apply dynamic programming. These are the very popular techniques which exist long back, and it is also easily available in any mathematics book. So if you try to solve your problem, which is large scale in nature and complex in nature, and if you solve that problem into linear programming, dynamic programming, it is difficult to solve the problem. For example, you can see if you go for linear programming, we know we deal with a large number of variables. For example, you are modeling a particular problem in which, let's say, there are 100 variables are required. So it is difficult for you to model these 100 different variables using linear programming. You have to take x1 plus x2, x3 up to, let's say, x100 and model it, which is practically not possible. And doing the optimization is also a very complex task. And sometimes what happens, we reach to a local optimum, although our objective is to reach to a global optimum, means the best one. but we reach to a particular point which is based in a particular place, but not overall, right? For example, you can say a student is securing good mark in computer science, but the student has not secured good mark in comparison to whole institute, right? That can be considered as a local optimum. So he's best in his class, but not best in the institute. Or sometimes what happen due to this complexity, uh, these optimization algorithm, if you want to do, then we have failed to solve these particular problems. Moreover, if you look into the objective function, so our objective is either to maximize or to minimize. Like if you take an example of a time, if you model your problem as a time, so time need to be minimized. But if you model your problem as a profit, so you need to maximize it. So optimization either focus on the minimization or focus on the maximizations. So, but when you model this, the objective function of this optimization algorithm, you will see these real life problems, their objective function is non-linear. So non-linear objective function case, it is difficult to solve the problem using traditional optimization method. So in order to avoid this one, we look into the solution using non-traditional optimization algorithm. So what this non-traditional optimization algorithm focus? It says that if you apply this particular to a particular scientific engineering application, then you reach to a near optimum solution. You may not get the exact solution, but your solution may be close to that particular solution. For example, if I say the exact value of a particular solution is 2.0, so when you apply these optimization techniques, non-traditional optimization technique, you may get a value like 1.999, or you may get a value 1.9995, or you will get a value 2.0001, something like that. So these solutions are called as near optimal solutions, which are uh, well accepted in the community, right? Although you are not getting the exact solution, but as you get a close solution, that is accepted. Similarly, if you go to the literature, if you go for the traditional methods, most of the traditional method case, we are applying heuristic. We are not applying meta heuristic. But these optimization technique, what we are looking here, they are meta heuristic in nature. So we should know what is the difference between a heuristic and a meta heuristic. So heuristic, you can say, it is providing a good solution for a particular type of problem. For example, let's say you are considering some autonomous vehicle system, and in which you assume that the road condition is good, and you want to apply some kind of optimization algorithm. Sorry, you want to apply some heuristics to solve that particular problem. So it may happen that your whatever the heuristic you have designed, the heuristic may provide good solution. But the problem of heuristic is that when the situation is going to change, it may not perform as well. Sometimes it is not giving you solution, or sometimes it is giving you very poor solution. So heuristic is based for a particular situation, not for every situation. But when you go for meta heuristic approaches, we expect to get a solution which is close to the optimum solution. That is the reason why we are looking for meta heuristic rather than a heuristic. So whatever optimization algorithms we will discuss, like genetic algorithm, let's say particle swarm optimization, ant colony optimization, or teaching learning based optimization, Jaya algorithm, or Rao algorithm, these all are coming under the meta heuristic based algorithm. Now, as I said that non-linear objective function, so let us understand what is the difference between a linear objective function and non-linear objective function, and why linear objective function case, linear programming is a best solution. For non-linear objective function case, this is not a best solution. So let us see here. Like if I compare the linear versus non-linear objective function, as you can see, here I have taken a x-axis and y-axis, and I have plotted a linear objective function and a non-linear objective function. So as you can see, In the case of linear objective function, optimum is always attained at a constant boundary. Okay, you will find optimum always in a particular boundary. And if you found the local optimum, you can claim that that is global optimum. For example, if you are solving a problem with linear objective function and you got a local optimum, and there is a sufficient proof that there is a this is a local optimal solution, then you can claim that that is also a global optimum solution. Okay, and as we say linear means if x is increasing, y is also increasing. Okay, if x value is increasing, then y value is also increasing. So linear means something related to the line, and we know y is equal to mx plus c. This is the straight line equation. So if you put a value of x, you will get a value of y, right? And m and c are called as your coefficients. One is called as slope, another is called as intercept, right? So it is more or less related to a particular line. But when you go for a non-linear objective function, the optimum may be the interior as well as the boundary of the constant. So previously it is in the constant boundary, but here it may be interior also. So as it is interior or in the boundary of constraint, local optimum if you are getting, then you cannot claim that is a global optimum, right? Like that here you can see also non-linear means we are not talking about a particular line, but we are talking about a curve, right? So in this way, the linear objective function is different than non-linear objective function, and most of the objective function which we are developing, they are non-linear in nature. That's why we are applying the meta-heuristic approaches or non-traditional optimization algorithms. So these non-traditional optimization algorithms are mostly inspired by natural phenomena. For example, somebody can watch how birds are flying. Based on that, some algorithm can be developed. Somebody can focus on how ant is moving. Based on that, some algorithm was proposed. Somebody can see that the behavior of a human, can also develop an algorithm based upon that. So most of the algorithm which were developed in non-traditional optimization algorithm, they are based upon the natural phenomenon, right? Like many recent algorithms, they focus on our teaching learning process. Okay, every day we are interacting with students, right? So teaching learning process case also, uh, we can see how a student learn and how a teacher teaches in the class. Based on that also people have developed some of the algorithms. But mostly stochastic optimization, all algorithms if you look into, they are stochastic optimization that uses the random number. Every optimization case, you will find a set of random number through that the particular algorithm is operated. Irrespective of the algorithm, you will find there is a random function. Maybe the range is different or same, okay, but we are using some kind of randomness. But objective of each and every type of optimization algorithm is to do two things. One is random search, another is hill climbing. Random search focuses on extreme exploration, whereas hill climbing focuses on extreme exploitation. So what is the difference? The difference is that one is trying to get the global search. For example, assume that in a particular area, you are searching a particular person, right? You are searching the particular person, and you have, let's say, some idea that the person is available in this particular area. Okay, so you have to look into different location in this area, which is a global search. At the same time, you have to also look into the local search, right? Suppose you got little bit hint that maybe that person is available in this domain, this area, then we perform the local search. So for every algorithm, you should go for the global search so that you will know what happened in other places also. At the same time, local search means in a particular area, I want to find that which one is best. Obviously, here you may get a solution which may be a local optimum solution, which is not same as global optimum solution. That may also happen, right? Because it is a non-linear objective function. The local optimum is not same as the global optimum solution. That also can happen, right? So our objective is to do global search as well as local search. But this is again a trade-off. So you have to balance these two in order to achieve a good optimization algorithm. Now, basically, we divide the optimization algorithm into three parts. One is called as evolutionary algorithm, another is called as swarm intelligence algorithm, another is called as other nature inspired algorithm. Okay, so whatever I have mentioned here in these three categories, so some of these algorithms we will explore as a part of this course. The rest of the algorithm you have to explore your own. Once you have expertise, you got some idea related to some of these algorithms, then you can explore other algorithms. So what we are going to teach here, under evolutionary algorithm, genetic algorithm is there, genetic programming is there, evolutionary programming is there, evolutionary strategies is there, differential evolution, bacteria foraging optimization, artificial immuno algorithm. These all are. This is also not the complete list. So we have so many algorithms under the evolutionary algorithm. But as a part of this course, I am going to teach you the genetic algorithm under the evolutionary algorithm. And coming to swarm intelligence algorithm, particle swarm optimization is also a very popular algorithm nowadays, right? If you are having a bi-objective function, bi-objective means if you want to achieve two different objectives at the same time, then you can go for particle swarm optimization. Similarly, artificial bee colony optimization, ant colony optimization, shuffled frog leaping algorithm, firefly algorithm, glowworm swarm optimization. These are coming under the swarm intelligence algorithm. And I think as a part of course, we are going to cover particle swarm optimization and ant colony optimization algorithm as well as firefly algorithm, right? Now, coming to other nature-inspired algorithm, we have simulated annealing, we have harmony search, we have teaching learning based optimization, which is based on our classroom teaching. We have charge system algorithm, we have central force optimization, we have cross entropy, we have cuckoo search, we have grenade explosion method, we have biogeography based optimization, we have Joya algorithm, and we have three variants of RAW algorithm, that is RAW1 algorithm, RAW2 algorithm, and RAW3 algorithm. So from these other nature inspired algorithm, we will discuss in this course, I think simulated annealing, teaching learning based optimization, and we are also going to cover this Joya algorithm and three variants of RAW algorithm, which were developed in the year of 2020. Okay, so you can see in your respective area what are the optimization algorithm already applied in your field, and once you make a good literature, then you will come to know that what are the other algorithms which we can apply in that particular field, and you have to show that by applying that particular algorithm, the performance of your problem is improving, or whatever performance metrics you have taken, they are providing good results. That is our overall objective. Okay, so this is all about the introduction of various optimization algorithm. So I'll more focus on now one of the popular algorithm, that is called a genetic algorithm. So evolutionary computing was started in the year of 1960 by I. Richenberg, and the first algorithm you can see, very famous algorithm, that is genetic algorithm, was proposed by John Holland in the year of 1975. He belongs to University of Michigan, right? But you can see once 1975, the first version, I can say, genetic algorithm also having several variants. Nowadays, people have applied genetic algorithm in different variants. But the very first variant started in the year of 1975. But after 11 years, two scientists, their name is Goldberg, another is called Samtani. In 1986, they applied the genetic algorithm in the field of structural engineering. So we know structural engineering is a part of civil engineering, right? So the very first application applied in the field of 1986. Although it is quite long, till now also many people have applied, many people are applying also, they have applied also genetic algorithm in their respective field. Only you have to see that what type of optimization algorithm well fit for your particular problem, right? So as I said, the objective function of any optimization algorithm is either to minimize it or you have to maximize it. Okay? Any particular problem, either your objective is to minimize or your objective is to maximize, right? Like I mentioned, time case, our objective is to minimize the time. If you say profit of a particular company, we want to maximize it, right? So for example, if you take a particular set A, okay, assume that that set A is having a set of element like this. Okay? Assume that these are the elements in the set, right? So if you find a particular element x0, okay, x0 may be anything. Okay, it may be this one. Okay, as I said, this is x0. Okay, I can say you choose any value that is xi. Let us take to avoid the confusion. If I take a variable xi, xi may be anything. Xi may be x0, xi may be x1, xi may be x2, xi may be x3. So if I calculate f of x0, okay, if I calculate f of x0, for example, suppose I am taking f of x is equal to, I am taking x square. So it is a function. So I will put what? First I will calculate f of x0, I will calculate f of x1, and I will calculate f of x2, and so on. Like that, you can take any function. So if you found a particular value f of xi, let it be xi, okay, f of xi, which is less compared to all other values. So whatever value you are getting here, right? Whatever value you are getting here, out of all the values, xi is the value where you got the least value. That is a minimization problem. Suppose here you x0 case you are getting 0, x1 case let's say you are getting 1, x2 case you are getting let's say 2. So out of this value, which case you are getting less value? Because it is a minimization problem. That's why I'm looking into the less value. So you have to find a xi so that f of xi is less than equal to f of x. So if it is true, then we call that is a minimization problem. But you have to take all the values that are available in the set x, right? Then we can claim that that problem is a minimization problem. But when you go for a maximization problem, similarly, you take a set of values, okay, and find a particular value where you can claim that f of x is less than equal to f of x0. For example, let's say f of x2 case, you got highest value. Okay, so I am considering this as a I, and I am saying I is equal to 2, where you will get the maximum value. All other case, you will get less value only. Okay, for all values belongs to A, then we call that problem as a maximization problem, right? So minimization problem case, we prefer the less value. Maximization problem case, we target the maximum value. That is our objective. Now, in case of genetic algorithm, we have set of questions. The first question is says, how variables in the genetic algorithm are encoded? Because in genetic algorithm, the very first phase is called as encoding. I'll tell you in the subsequent slide, but I want to show you what are the major challenge in the case of genetic algorithm. And encoding may be different. Like most of the research article, they do encoding either binary or they go for decimal. But you can also try the encoding with octal number system. You can do with hexadecimal number of system, right? Although all are equivalent to each other, but we can represent in a different way. So based upon the type of problem we are dealing, suppose your values are coming a very long value, and we know if you go for hexadecimal representation, it will be converted to a small value. Okay, if you take a binary value of 32-bit, we can squeeze it to a hexadecimal. Let's say if 4-bit represents one hexadecimal, then with 8 hex digit I can represent it. So the first question arises, how these variables in the genetic algorithms are encoded. The second question arises, how fitness function is calculated. So till now, I told you two things. One is objective function, and I told you encoding, but I have not told you fitness function. Now there is again a difference you should know. what is the difference between a fitness function and the difference between a objective function. And is it possible that fitness function is same as the objective function, right? That we'll discuss in the subsequent slide. Then there is a step in the genetic algorithm that is called as selection. And there are several methods we have. Right, like I mentioned, encoding case also you can go for different method. Fitness function also you can choose different functions, like x square is a function, log x is a function, sin x is a function, 10x is a function. Everything is a function, but which function fits to your problem, that only you have to try, right? Similarly, in the case of selection methods, we have several methods. What are the methods? We have Ruler-Thiel selection, we have Boltzmann selection, we have tournament selection, we have steady state selection. Although Ruler-Thiel selections are also having subsequent improvements that I'll discuss in the later slide. So which selection method you are going to choose for your optimization? So it is very difficult to determine. Right, this is just like hit and trial method. You try with 4-5 selection methods, and suppose you found that Ruler-Thiel selection is better in comparison to other selection. Then you have to choose that particular selection method. After that, there is another interesting thing: population of mating pool. That is called as reproduction. In genetic algorithm, we took two per population, and we generated two children, right? So mating pool is nothing but a group of population, a set of population is called as mating pool. So in the mating pool, you are selecting two different population and generating more population, right? So how to do this one? Which two you have to choose, and how to generate these children? So these all are also a challenging problem. Apart from this one, there are several type of operators we are using. We call that operator as inheritance operator, which is applied to the mating pool. What are the inheritance operator? For example, you are applying, let's say, the process of crossover. I'll tell you these terms later. So these terms maybe, if you are new to this genetic algorithm, maybe this inheritance operators, whatever I'm saying, it is also new to you. So crossover is a operator. Mutation is a operator. If you negate 0, if you, let's say, take complement 0 to 1 and 1 to 0, that is also inheritance operator. So there are several type of operators we have that we have to take to perform or to generate different populations, right? Now, some of the major questions related to genetic algorithm is that, does an optimal solution exist? Suppose you have taken X is a problem. So I have a problem that is X, and you have decided I am going to solve this X. I want to solve this problem X using genetic algorithm. So if it different, definitely you are going to ask, does an optimal solution exist for this particular problem? Okay. Suppose your answer is yes. So obviously your answer is binary, either yes or no. If you say that yes, there is an optimal solution exists, then the question arises, is it unique? There are many ways we can get an optimal solution. Okay. For example, there are, let's say, 3 ways to get the optimal solution. You can follow a particular process, let's say X, another process say Y, another process, let's say Z, to get the optimal solution. Or is there only one way to get that particular solution? That's why it is asking, is it unique? Now, if it is a unique solution, or let's say multiple solutions are exist, so what is the procedure to get it? What process you need to follow to get that unique solution? Next question arises, how sensitive the optimal solution is. For example, you are giving, let's say you have taken a machine as an example. Take a machine as an example. Let's say this machine takes 2 parameters. One is X and Y. And you got result, let's say Z. Okay, so you observe that, let's say value is 0.2, you have taken here, you taken 0.3, and you are getting, let's say, value 0.5. Okay. Let's say you are trying with another value, right? Instead of 0.2, you are taking, let's say, another value 0.9. Here you are taking 1.5, and you are observing Z. So what we want to actually find, for what particular range it is performing well, and for what particular range it is not at all performing well. That means we want to find what is the sensitive, whether our solution is sensitive to a particular range of value. If we change that particular value, whether it is going to give a good value or not, that we are more concerned. That's why it says here how sensitive the optimal solution is. Okay, and how the solution behaves if there is a small changes in the parameter. So if you change it, whether it is sensitive or not, or the small changes impact our solution largely or not, that also you need to address in the case of genetic algorithm. So when to apply genetic algorithm, that is more important. Irrespective of research domain, you cannot apply the optimization algorithm. Okay, simply applying optimization algorithm is not at all a solution. Okay, so what way we can solve this particular problem? Okay, let us see. For example, I am taking an example. Let us take two computer systems. Let me call the first system as A, second system is B. Okay, and let's say I have four different work: W1, W2, W3, and W4. So number of work is 4 and number of resources 2. Okay, so how many ways these works can be assigned to the work? These works can be assigned to the machines. Can anybody say how many ways you can assign these works to two different resources or machines? What are the number of ways? Can anybody guess? Yes, you are correct, Jasmini madam, right? It is 2 to the power 4. Okay, that is 16 different ways. Okay, but if I take the same problem by considering 16 different, let's say computers, 16 different computers, and 512 number of works. So what it is coming? It is coming 16 to the power 512, right? If you go for 16 to the power 512, you know 16 to the 512 is much greater than 10 to the power 512. Why I am writing 10 to the power 512? Because it is, 1 followed by 512 number of zeros is nothing but 10 to the power 512. So imagine if a particular solution takes 1 second time, okay, or 1 millisecond time, or 1 nanosecond time, imagine to check 10 to the power 512 number of solution, how much time is required. In fact, if you calculate, you will see you will not get a solution in your lifetime. A human being cannot get a solution in his lifetime. So those problems where you have a very large space, there only you have to apply optimization algorithm, genetic algorithm, particle swarm optimization, and whatever optimization algorithm comes to your mind, that is applicable when the source space is very large. So, but when the source space is very small like this, like I am concentrating on only two machines, 4 different work and their assignment, don't apply any optimization algorithm because it can be solved using other methods. So there is no need to apply any optimization algorithm to solve this particular problem. So you can see here what is written here. Genetic algorithms are good at taking larger, potentially huge source spaces and navigating them, looking for a optimal combination of things and solution which we might not find in a lifetime. In our lifetime, if a problem cannot be solved, so meta-heuristic approaches or optimization algorithms can be applied in that case. So other case, don't apply them genetic algorithm or particle swarm or any optimization methods just to do some kind of research. So you have to claim that yes, optimization algorithm is really essential for this type of problem. So three most important aspect of genetic algorithm is that, as I already said, one is fitness function, another is objective functions. You can take both are same or different, that we'll discuss later. Another one is called a genetic representation, another is called a genetic operators. So early days, if you see initial variants of the genetic algorithm, there are so many options, so many operators are there. But later point of versions, people have stick to 3-4 operators and they perform the operation with respect to that operators. But you can apply any number of operators throughout the lifespan of the genetic algorithm, or I can say a particular single round of iteration of a genetic algorithm. So what are the operators we have? So here you can see inversion is an operator, dominance is another operator, deletion is another operator, chromosomal duplication is another operator, translocation is another operator, segregation, speciation, migration, sharing, and mating. These all are called as your inheritance operators. But out of these operators, we are only concentrating on very few operators, right? One of the three popular operators, you look into the number of operators are there. I am not listing all the operators here, but three basic operators that we are going to use in the recent variants of the genetic algorithm is that one is reproduction, another is crossover, another is mutation. Okay. So first we'll apply the process of reproduction, then we'll go for crossover, then we'll go for the mutation. So for every iteration of the genetic algorithm, you have to repeat these three operators, right? Now, what we are going to discuss in the rest of the time, we'll look into, you can look into this particular flowchart, which I am going to discuss in the subsequent slides. So first let us understand the process of genetic algorithm. The first one is called as initial population. Okay. The very first step is called as initial population. For example, if you solve your research problem and you found that yes, genetic algorithm is really required for your research problem, right? So you have decided to apply genetic algorithm. Now the first question arises in your mind, how many initial population I will take? So what is a population? Population is a solution. For example, for a particular problem P, you have number of solutions. X1 is a solution, X2 is a solution, X3 is a solution, X4 is a solution, and so on. Right? So how many? X1 is also a solution. Maybe X1 is a better solution than X2, or X2 is a better solution than X3. But they are the solutions. We are not talking about which one is a good solution and which one is not a good solution. Right? But how many such solutions you will take initially? So that is an interesting question. Okay. And nobody solved this particular question till now. But usually what we are doing, we generally take 100 populations. Some people take 50 initial populations. But why they are taking 150? There is no answer for it. Right? So there is a usual practice that people have used 100 or 50. If you say that why I want to take 200, you can take, there is no issue. Right? So once you have taken this 100 or 50 population, there is a process called a selection. Okay. What selection will do? Selection will choose some of the best solutions. Okay. So how to know out of these 100 population? For example, let us stick to a particular value. Let us take this is 100. So out of 100, suppose I want to choose only 10 population in the process of selection. So the question arises, how to choose 10 population out of 100 solution or 100 population? Like in a class, assume that 100 people are there. Okay, 100 students are there. But you want to select only 10 number of students. You want to select only 10 number of students. You don't want to consider the rest 90 students. So what you will do? You can conduct a test, right? You can conduct a assessment test, or in interview process, people do written test followed by let's say interview, right? They interacted and finally selected only 10 candidates. So there is a function, okay, which we call as fitness function, right? That fitness function will help you to say that whether a particular population is fit for your problem or not. So you have to design a fitness function. You have to find the fitness value of each and every solution, starting from 1 to 100. Okay. You have to calculate for each and every solutions. After finding the fitness value of each and every solutions, you have to shortlist how many solutions? Only 10 solutions. Okay. You may choose, for example, base 10 value. In the case of minimization, you will choose the lowest 10 values, or in the case of maximization, you will choose the population which are which are generating a highest value, right? On that way, the process of selection is carried out. But why I have taken 10? Again, there is no question. Okay. If you put a question, there is no answer. Right? There is nobody solved that why 10 population is required out of 100 or 20 population is required. So that is really challenging. So whatever the number of population you have selected, that we call as new population. Okay. And you can see this particular process starting from initial population to new population. This is done only one time. Initial population, selection, new population. That is done only one time. It is not repeated throughout its life cycle. But here you can see, if you see, here you can see there is a loop. Like I can move like this. I can move like this, right? So there is a iteration here. So this process of iteration will iterate until unless your condition is satisfied. So you will repeat this process until unless your condition is satisfied. So we put some kind of condition. So the condition is also not unique. Many people have used different type of condition. For example, I can say you run your genetic algorithm for 20 iterations. 20 iterations. After 20 iterations, whatever value you are getting, you have to accept that value. So your termination condition is 20 iteration. Somebody can choose another one. Somebody can say that in 2 successive iteration, if the value is same, like if you go for Newton-Raphson method, which we have seen in engineering mathematics, Newton-Raphson method. So in Newton-Raphson method, in a particular iteration, let's say iteration I, you are getting a particular value. In iteration I plus 1, you are getting another value. If the value is same, then we'll stop here. If the value is not same, then we'll go for iteration number I plus 2. Until unless, until unless in 2 successive iteration, if the value is not same, we have to iterate it. Okay. So in 20 iteration, after 20 iteration, I can terminate. So whatever may be the termination condition, if the termination condition is satisfied, then your process is completed. Okay, let's say after 20 iteration, whatever value you are getting, with that value, you are going to terminate from that particular loop. But if termination is not satisfied, so what you will do? You will go for a process of crossover. That's why in the previous one I told you, crossover is a inheritance operator, followed by we apply a process of mutation. Mutation is also a inheritance operator. But as mentioned in this flowchart, you can see crossover is always applied to whom? Crossover is applied to the parent. However, mutation is always applied to whom? It is applied to the children. So there is a misconception that we took 2 parents, perform crossover, perform mutation to generate the modified children. But that is wrong. The process is that crossover is applied to the parent, mutation is applied to the children to generate the modified children. Right? And once you generate these modified children, we'll check the fitness. If the fitness is satisfied, then we declare that children as fit children and will add into our new population by replacing the old population. But if it was found that modified children having not good fitness, so what we will say, we will take that as a unfit children and we will discard it and we will continue with the next iteration. So I think there is a question. Let us take that. Yes, madam, Madhvi, madam.
Sir, the selection, we do
Yeah.
it only once, but
Yes.
the from the selection in the new population, there are no crossovers and no mutation. So can you please explain this part of the concept?
Can you please repeat your question, madam? Selection is done once. That is okay.
That is what you explained. Selection is done only once,
Yes.
and the new population that is there, what does it consist of? If fit children are entering the new population,
Hmm.
then what is coming from initial population to the new population? All parents.
Suppose I have taken 100 population. Okay, I have applied a process of selection and I am selecting, let's say 10 population, 10 best population. That 10 population is placed in the new population.
So selection has nothing to do with crossover or
No,
mutation. It's just selection.
selection has no role. Selection, that selection which comes to your mind, there is a process we are doing here that I'll tell you in later point of time.
Yes, sir. Got it.
That I'll tell you. So
Yes.
for you are right, for first iteration, before first iteration, in selection process, whatever 10 population we got, that is same as new population. But in iteration one, after one iteration, this new population, what is available before applying particular iteration, which is different from after doing any iteration. For example, here I have taken 10 iterations. Okay, sorry, 10 different population. Okay, so when I do one particular round, there is no guarantee that these 10 population will be there. So it may happen that 5 different populations are replaced with another 5 different population. So this selection process we are doing once only. But what you are saying, there is a process also involved here that is called as not called selection, but there is a process. For example, if there are two parents, right, and two parents generate two different children. So total number of population here it is 4. But we have to choose only 2. We should not choose 4. So which 2 is going to be choose? That is based upon the fitness. So we'll check the fitness. Based upon that, 2 population will choose and enter into the new population.
So the iterations are not by n equal to 1, 1 plus 1, 1 plus 2. This iteration is selections.
Iterations are selections.
Selections, because you said 2 children going to 2 parents giving out 2 children.
2 parents will generate 2 children.
Yeah.
Okay. Then we'll go for 2 modified children. By modifying something in the children part, we'll go for 2 modified children. Then we'll compare with the parent. For example, parent 1 is going to be checked with the modified children 1. Okay, and parent 2 is going to be checked with the modified children 2. Assume that the parent 1 performance is poor in comparing to modified children 1. Then I am selecting modified children 1. On the other hand, let's say parent 2 is better than modified children 2. Then I am keeping parent 2 as it is. Only thing is that here, after doing this process, we'll replace parent 1 which is already there in the new population with modified children 1. Okay, this process we are adopting here. And this entire process is called as one iteration.
Okay, sir.
Okay, I'll tell you with an example. Okay, later slides I'll tell you an example. I think that will be make more clarity about this particular question. Okay, now what is a sort space? As I said, the space for all possible feasible solution is called as our sort space. Yeah, madam, if you have any question, you can ask.
Sir, in the previous slide, we are selecting the new population. There are two procedures. We go to terminate. If it is yes, we end that procedure of genetic.
I think the voice is breaking, madam. Can you write in the chat box?
Okay, sir.
Yeah, you write in the chat box. I'll address it.
Okay, sir. I'll write it. So you can explain.
Okay. So the space for all possible feasible solution is called a source space. Okay, generally we consider a particular source space in which we want to find a solution. So solutions may be available in different places, and in one place you will find global optimum, and one of the place you can get local optimum, and so on, right? And each solution can be marked as a fitness value. As I said, every solution you will get a fitness value. Like in our education system, every student is getting a CGPA. Right? You can say one student is having good CGPA, another student is having poor CGPA, but everyone is having one CGPA. One solution may be good, one solution may not good, but everybody is having a fitness value. So looking for a solution means looking for the extreme. So if your objective is to go for maximum, So we are moving for that. If our objective is to minimum, we are looking for that. Okay, there is a question by madam, how to conclude with whether we require crossover or mutation. Madam, we need both crossover and mutation. We are performing crossover first, then whatever resultant we got after crossover, that we call it children, then we apply mutation to the children. I'll show you an example in later slide so that these things will be more clear. Okay, so when source space is complicated and we don't know where to look for the solution and where to start, and it is a very big space, so not only genetic algorithm, any nature inspired algorithm can be applied into that particular field. So let us consider a on-constraint optimization problem. Here our objective is to maximize f of x. Okay, I am taking a function f of x. Okay, our objective is to maximize it. And I want to find a source space, right? You cannot say that x value may be anything. So anything means it is minus infinity to plus infinity, right? So it is not possible to check with all possible value. That's why we put a limit here. That is, the x value is between a lower limit and a upper limit. For example, I can write minus 5 less than equal to x less than equal to plus 5. Right? So my source space is within minus 5 to 5. What I want to say that within this source space, you will get a solution for f of x. But sometimes what happens, problems are always not given to you for maximizing it. Sometimes our objective is to minimize it. So in that case, what happens, you can convert a maximization problem into minimization problem, or a minimization problem into maximization problem as well. For example, if your objective is to minimize f of x and f of x value is greater than equal to 0, then if you want to solve it, it is fine. Otherwise, if you want to convert it into a maximization problem, you can do by 1 by f of x. But f of x value is greater than equal to 0. So greater than equal to 0 means f of x the value may be 0 also. So 1 by 0 means it is again not defined, right? That's why we are adding a plus 1 in the denominator, right? So what I try to convince you here, you can convert a maximization problem to minimization problem by taking its 1 by that particular function. In that way, you can convert a minimization problem to a maximization problem. But whenever f of x value is equal to 0, so you can say maximize minus of f of x. That can be done to solve a particular problem. So it is not necessary to solve a problem with maximization or minimization. You can convert either maximization to minimization or minimization to maximization based upon the requirement. Now, there is a very famous problem that is called as knapsack problem. Okay, knapsack means there is a bag, right? So in a particular bag, it is having a capacity. Let's say bag capacity is 5 kg. Okay, you cannot keep the items more than 5 kg. So you visited a shopping mall. In the shopping mall, there are several items are there, and each item has a value and each item has a size. For example, 1 liter. Let's say one item is there, that is 1 liter. Let's say the cost is 100 rupees. There are several items are there. So what you have to do, you have to, let's say in that shopping mall, assume that for a simplicity, we assume that in shopping mall only 12 items are there. Okay, only 12 items are there for easy calculation, right? So I am, if I go for the first chromosome, these chromosomes are called as population or solutions, you can also say. For example, if you go for first chromosome, what it says, you have to, if it is 1, that means that item you need to put into your knapsack, means your bag. If the item is 0, you have to skip it. For example, here you can see, I am going to take the first item, third item, fourth item, sixth item, seventh item, and let's say 11th item and 12th item. So I want to take how many items here? I want to take 7 items. So let's say the sum of these 7 items is 5 kg. Okay, it is not exceeding 5 kg, so I can say less than equal to 5 kg. But another person is also having the same type of bag, whose size maximum carrying capacity is 5 kg, but that person has selected the second item let's say 5th item, 6th item, let's say 9th item and 10th item. Okay. So different people are taking different item based upon their capacity, right or not? So you have to put the items in such a manner that it will fill with 5 kg, and number of items what you are putting, their value is, let's say, minimized or maximized, for example. Okay. So when we talk about value may be minimized and value may be maximized, right? So you have to generate different type of chromosome to provide the solution. So this solution is this chromosome A is also giving a solution, chromosome B is also giving a solution. But after analyzing A and B, you can find that A is better than B or B is better than A, right? But every chromosome is providing you a solution. Sometimes what we are doing, we generate a 4-bit binary string that can be used to represent the numbers, right? So I can represent different representations which we have studied in binary number system, whether it is a binary or octal or hexadecimal or decimal. In that way also I can represent the number. For example, see these examples, the idea will be more clear. So let us consider there is 2 variable function. One variable is x1, another is variable is x2. And each and every variable is represented as a 4-bit binary. Means x1 is represented as a 4-bit binary, x2 is also represented as a 4-bit binary. So what is the possible values? The possible value for x1 is any value between 0, 0, 0, 0 to 1, 1, 1, 1. If we assume that it is a 4-bit number, 4-bit binary number, then definitely maximum value is 4, 1, minimum value is 4, 0. Similarly, if I take for x2, the same thing, 4 zeros to 4, 1. So what I can say? I can say the lower limit is 4 zeros, where upper limit is 4 ones. But here, it is pretty clear. For example, if I represent it by 0, then I'll go 0 up to 9. Then in hexadecimal system, we use A, B, C, D, E, F, right, to represent it. So it is very clear. But not necessary every time you are given the range 0 to 15. Okay, this is the range from 0 to 15, right? So not necessarily always you will get a range of 0 to 15. Sometimes you are given the value as 2 to 17. So in that case, what happened? 2 will represent 4 zeros, 17 will represent your 4 ones. Okay, so this is the particular formula which we can use to find the decimal equivalent of a particular binary number. Right? If x limit is equal to 2 and x upper limit is 17, so for a particular binary string, you can determine what is its decimal equivalent. Okay, so it is not necessary to code all variables with equals of string length also. Like we have seen different kind of coding. Like you have, if you remember, there is a tree-like coding. Okay, the variable which is frequently used, okay, can be given with a small code. For example, 2 is repeatedly you are retrieving, so you can represent 0 to represent 2. Whereas let's say 17 you are not calling repeatedly, so you can put a bigger means long number of 4-digit number, right? 4-bit of number. Okay, so those numbers which are frequently called, that you can represent in less number of digits. Okay, maybe 1-bit or 2-bit or 3-bit, and those numbers are not frequently called, that also you can represent in 4-bit number, right? So in that way also you can represent different types of numbers. Like here you can see, here xi need not be equally distributed also. For example, I have taken 1 to 16. Okay, 1 to 16 means 1 I am representing by 4 zeros and 4 1 represent the 16. Or you can take 0 to 15 also, no problem, right? So the decoded value is 0 to 15. So you see, 0 indicates the fiber angle is 0. 1 indicates the fiber angle is 10. So difference between these two is 10. 2 case, it is 10 to 20. So it's again difference is 10. 20 to 30, again its difference is 10. What about 30 to 45? The difference is 15. Similarly, if you find a difference here, 90 to 100 minus 10, the difference is too much, right? So not necessary they are equally distributed, not necessary the same bit of binary string you will use to represent a particular number. So whenever you are going for encoding, based upon your requirement, you can choose any type of encoding. For example, here you can see I am showing you octal system. Earlier I told you a binary system, right? Now I am showing an octal system. Octal means what? 8 values. 8 values means value starts from 0 and ends with 7. Hexadecimal means value starts with 0, ends with F. So that is also different type of encoding schemes that you can use to represent the genetic algorithm. Okay. But mostly people use binary system. If you go for any research article, you will find they are using binary system. So even if there is a 16-bit, we are representing 16-bit to show that this is our chromosome. Okay. So instead of showing the 16-bit one, you can represent in a 4 hexadecimal digit. That is a better way of representation. Now, there is a very famous problem in mathematics and computer science that is called a traveling salesman problem. So traveling salesman problem says that if there are n number of cities are there, right, assume that n number of cities, a salesperson has to visit these n number of cities. Okay, and it has to start with one particular city, visit any city. Okay, any city it can visit, but it should visit one city at least once. Okay, at least once, at most once, or that means exactly once. For example, it has visited this particular city. After that, let's say it is visiting here. After that, it is visiting here. Again, let's say it is visiting here. Then it is visiting here, and it is reached to its source. Source and destination is same. Okay. So traveling salesman problem means you have to visit number of cities exactly once, and you have to return to the cities where you started your journey. So assume that total number of cities you want to visit is 9. Okay. So there is a chromosome representation. So in this chromosome representation, first what you have to check? You have to check that if there are 9 number of cities are there, they are represented as 1, 2, 3, 4 up to 9. Then you have to check that all the cities should be visited once. So you can see 1 is there, 2 is there, 3 is there, 4 is there, 5 is there, 6 is there, 7 is there, 8 is there, 9 is there. So all cities are covered under chromosome A. So that means this chromosome is a valid chromosome. And every population, as I said, it may be a good, it may be a bad, but they are giving you a solution. But instead of 6, let's say I am putting here 7. So 6 is missing in chromosome A and 7 is repeated twice. What it indicates? This population or chromosome is not a valid chromosome. But whatever chromosomes we have in initial population, they are valid chromosomes, right? So the genetic operators correction must be made to leave the chromosome consistent. Okay. If there is any problem we have, then what you have to do? You have to make genetic operator corrections. Right? For example, here as I said, if 7 is repeated twice, what will do? You have to replace it with the 6. Otherwise, this chromosome you have to discard from your initial population. So, irrespective of anything, you have to find it is a valid chromosome. Otherwise, it is not going to be accepted. Okay, like that, not necessary you will. Yeah, madam. If you have any question, you can ask. Okay. So not only chromosomes takes binary system, or you can say octal or hexadecimal system. Sometimes we take real number also. Right here you can see set of real numbers. Sometimes we take some alphabets also. Sometimes we take some kind of actions also. For example, if you go for a robot, let's say robot case, we can move left, right, back or forward. So that can also be considered as a action. Okay. Similarly, we know nowadays the deep learning is much more popular. Machine learning is also popular. People are applying neural network and other things. In neural network, we have weights, right? These weights is there in between input to the hidden layer and hitting to the output layer, right? So the weights can be updated, right? Initially, maybe the weight is 1.234. Later point of time, you can update that particular weight, right? So different, if you generate different chromosomes, so every chromosome is just generating different type of different weights, right? For a particular weight, maybe your neural network performance is better. So there also you can generate different type of weights and generate different type of chromosomes to check that which set of weights can perform better in the case of genetic algorithm. So many people also gone for tree coding, okay, or they go for prefix and postfix notations also. For example, you can see x plus 5 divided by y. So you can represent plus. If you do here that this is a infix notation. If you go for prefix notations, so I can write it is a slash 5y, then x plus. Then if I apply, then again it will be converted to plus x slash 5y. So that also can be represented. So with this, what I want to convince you that for any type of functions or any type of commands, any type of weights, if you want to apply, there also you can apply genetic algorithm and map it and perform the encoding. Because finally, first you have to do the chromosome representation, right? That chromosome encoding is possible for any type of problem. Okay. Now, as I said, fitness function. So generally, if you go for genetic algorithm, early days it is only suitable for maximization problem. That's why I told you there is some, if there is a minimization problem is there, what we are doing, we are converting it into a maximization problem. So for example, you can see if there is a function f of x is there, so we are converting it to 1 by f of x. The GA is only suitable for maximization problem. So minimization problems are converted to maximization problem. And as there is a chance that f of x is equal to 0, so we are adding an extra one whenever we go design the fitness function in the genetic algorithm. Okay, let us take a small problem so that whatever idea we have discussed till now, I think it will be clear with this example. Let us take a objective function which takes two different variable. One is theta1 and theta2, and function is pi. So what you have to find? You have to find pi of theta1 and theta2, right? Okay, so here, if you get the value of theta1 and theta2, and if you put in this objective function, it will be solved like this. You have to find minus 4 sine theta1, minus 6 cos theta1, minus sine theta2, minus 2 cos theta2. Right? So the range of theta1, theta2, that also you need to mention, because source space should not be infinite. You have to say that within a particular source space, it is a large space, no doubt. But within that large space, you have to find a solution. So theta1, theta2 value is in between 0 to 90. So what may be the value? The value may be 0, the value may be 90, the value may be 45 or 90. So as it is a range of 0 to 90, okay, if I want to represent in a 4-bit string, what I will do? So, you know, if I go for 4-bit string, so 90 this should be divided by 15. Okay, because 4 zeros case it is 0. That's why I'm taking it is 15. Okay, so I'll get 6 degree. So every 6 degree I have a solution. For example, 0 is represent 4 zeros and 6 represent 0, 0, 0, 1. So when the value degree is in between 0 to 6, either you can map to 4 zeros or you can map to 0, 0, 0, 1. Right? So we consider 6 degree. Each 6 degree, one particular code. So see this example. What it indicates? 4 zeros indicates the angle is 0, where 4 1 indicates the angle is 90. Okay. And as 90 divided by 15 is equal to 6. So every 6 degree, as 6 degree, you have a binary coding scheme. Okay. Now, how to find a solution? See here. For example, assume that the fitness function f, the fitness function f is nothing but f dash minus 7. The fitness function is f dash minus 7. It is assumed. You can take f is equal to f dash minus 10. You can say f dash is equal to f dash square and minus 7. Anything you can take. Okay. F is equal to f dash minus 7. And f dash is considered as minus f. So it is considered. It is an assumed. So it is minus f and minus 7. For example, now we go for first phase, that is called as initial population. So initial population case, we have two parameters. One is theta1, another is theta2. Theta1 can be represented as a 4-bit binary. Theta2 is can be represented in another 4-bit binary. So for example, I am taking the number of initial population is 8. For an example, normally we take more than 50, right? So for example, first population says that all zeros. That means theta1 case all 0, theta2 case all 0. So we know f is equal to minus f minus 7, which is equal to minus f minus 7, right or not? And this f is nothing but minus 4 sin theta 1 minus 6 cos theta 1 minus 4 sin theta 2 and minus 2 cos theta 2. So if I put here, you can see this pi of theta 1 and theta 2 is placed on by replacing f. Okay, minus this one minus 7. And pi of theta 1 theta 2 is minus 4 sin theta 1 minus 6 cos theta 1 minus 4 sin theta 2 and minus 2 cos theta 2. So what is the theta 1 value? 0. You know sin 0 value. If I put here also 0, you know what is cos 0 value. If I put 0 here, you know what is sin 0 and what is cos 0. So if you saw, you are getting the value as 1. Right? Similarly, the second population case, what you will do? F is equal to f dash minus 7. Okay? And f dash is equal to minus f minus 7. What is f? F is nothing but minus 4 sin theta 1 minus 6 cos theta 2 theta 1 minus 4 sin theta 2 minus 2 cos theta 2 minus 7. Now, what is the theta 1 value? Theta 1 value is 0, 0, 1, 0. You see the 0, 0, 1, 0. What is the corresponding value? 12. So, you need to find sin 12 here. You need to find cos 12 here. What is the second coding? Second coding is 0, 0, 0, 1. So, its corresponding value is 6. Right? So, you have to find 4 sin 6 and minus 2 cos 6. So, if you calculate and solve this using calculator, you will get the value as 2.10. Okay, like that we can take any number of population, but for the simplicity of example, what we have taken 8 different population and we have calculated their fitness value. Okay, so if anybody will ask you, let's say this is a minimization problem. This is a minimization problem, right? So which solution is better? Can anybody say out of these 8 population, which population is better if it is a minimization problem? Which solution is better?
First one.
First solution is better because that is generating the less value. Similarly, I can say, let's say highest value is I think 4.66 if I am correct. So fifth pop solution is better in the case of maximization. Right. So as I said, I will tell you what is the difference between objective and fitness function. Always remember, objective function is you have to optimize. Optimize means either you have to minimize or you have to maximize. But fitness function will guide you throughout the optimization. Now, with looking into this fitness value, you can decide whether to stop or to continue, whether to pick a solution or not a pick a solution. That means it is guiding to the process of optimization. But objective functions are not meant for that particular one. It is meant for doing optimization, to minimize or to maximize. But the good thing is that in many cases, we can take objective function is same as fitness function. Whatever objective function you have taken, that also I can take as a fitness function. For example, yeah, madam,
Sir, please explain the difference in fitness function and optimization function.
Suppose you have a function f of x, right? F of x is equal to x square. Okay. Suppose your objective is to maximize in a particular limit. Okay. So this function is treated as your objective function, because objective function is a function which you have to use for maximization or minimization. Okay, your objective is to either minimize or maximize. If I assume that it is maximization, so this is treated as an objective function. Okay, but what is fitness function? So for this, you will take set of chromosomes or populations. Like here we have taken 8 population. So you can take 8 population for this particular function, right? So you are evaluating out of these 8 population, which population is better. So either
Suppose,
you
sir,
can,
we get two of them who are 4.66 or like 4.65. Are we looking at the reliability after optimization to talk about fitness?
no, fitness function case, we are looking which value is better, which value is not better.
That is optimization itself.
Optimization,
What
optimization
I
comes,
had, what I thought was, when you talk about fitness, is the robustness of that solution. So even if you have one solution is 4.66
uh,
and the other solution 4.65, suppose,
okay, okay.
then if the parameters are sturdier or
Hmm,
robust, or
hmm,
like we have in our even in your, when you calculate your R square for a regression,
yes,
the better R square, then you say, yes, this is significant to a third level. So is that the function of fitness function? Right now, the distinction is not showing. You
okay.
just now said that we, since we don't have a distinction or we don't have any other things, like even in on Amazon you have 3 star, 5 star. So 1,000 people have given good reviews.
Hmm,
So
hmm.
the 1,000 people giving 3 star and 5 people giving 3 star, reliability is higher for the 1,000
Yeah,
people. So
yeah.
is that the fitness function which is not showing out here?
No, no, actually what we are doing, what you said that is correct only. Maybe in 4.66 case, as you said in rating case, let's say 100 people rated it. 4.65 case, let's say 10,000 people rated it. So this solution is more reliable in comparison to that. That is also correct, whatever you said. But what we are doing in the case of optimization, we are not taking only one value. Generally, whenever we are taking a set of values and do a couple of iterations, then in the final iteration also, we choose a set of value and find its average value to say that which value is better. For example, if you go for this particular example, after let's say 10 iteration case, you will see more or less these values are close to each other. Like you mentioned 4.65, you may get 4.67, 4. Let's say 61, something like that. So
Yes,
we normally took a set of values and find its average value to say that this is the final solution. We are not relying on only one solution.
perfect.
Okay.
Perfect.
Yeah. There is another question. How you took different value of theta 1 and theta 2? This is completely random, madam. Whatever you have mentioned, these values are completely random. And whatever populations I am taking here, if I write a code also, as if there is a randomness is present, you may not get the same values also, right? So we never take a particular value in optimization. Every iteration case, you will get different values only. Okay. So the next is we will go for the process of selection. So here you will see a couple of selection methods. I'll tell you some of the selection methods so that the idea will be more clear. So the overall idea of going for selection methods is sometimes what happens. Like some people also asked what is the difference between initial population, then selection, then new population. So many research articles also suggested that you take initial, if you are taking initial population is 20, after selection also the number of population is 20 only, right? Suppose I am taking 20 populations and I am evaluating their fitness. Obviously some of the fitness is good, some of the case fitness is bad, but in the process of selection, what I am doing, I am generating 20 populations, means output of the selection process is 20. So what actually we are doing, we are creating multiple copies of the same chromosome. Okay. So for example, one particular population is performing well. So I am taking it's a two different copy, right? If a particular population is not good, I am going to replace it. So that also you can see in the different type of processes. So the idea will be more clear. So we'll go for these particular methods. So let us start the first method that is called as roulette wheel selection. So in roulette wheel selection, as the name suggests, there is a wheel. Like in Play Store also we have a game, right? So you simply roll a particular wheel and there is a marker. Okay. So after a few seconds, your that wheel is going to wheel is going to stay in a particular location, and they will look into the marker where the marker is pointing. So that is considered as our solution, right? So what we are doing? So in this case, you see, already we have seen we have taken 8 different population, right? And these are the encoding for 8 different population, and their corresponding angles, right? And we have calculated we have calculated the fitness, right? These are the fitness value. So we can calculate what is the average fitness value. Okay, like class, we also calculate average score to say that those students who secured more than average, they are okay. If they are securing less than average, they are below average, right? So if you sum all these values, you will get 23.27. And as the number of population is 8, I am dividing it by 8. Just a mean calculation. So you are getting 2.908. So in relative selection, what we are doing, we are calculating probability of ith chromosome or ith population. So how to find the probability of this one? If you know total probability is always 1 or 100%, you can say, right? So once you calculate the cumulative value, if I divide it by individual fitness, for example, individual it is 1, right? 1 divided by its whole value, not the average value, the total value, that is 23.27. So we are getting 0.0429, that is around 4%, right? Similarly, if you take this particular case, okay, this particular case, it is 4.66, okay, it is 4.66. So what I will do here, 4.66 divided by 23.27. Okay,
16.
so its value is, you will get 0.2. Here and there may be a slight change. Okay, there may be a minor change in the third or fourth digit. So we are getting 0.200. So if you calculate some of these values, you will get the probability is always 1. So why you are calculating this probability? Because finally you have to represent in the form of a wheel. Okay, so here we are taking ceiling value. So here this 4%, 4.29% is also considered as 5%. So population 1 covers this much area in the wheel, right? Similarly, population 2 covers this much, 3, 4, 5, and you can see which population is having more probability here. I think these two, right? Population number 5 and population number 8, right? So you can see here, population number 5 case it is 20%, and population number 8 is 20%, right? So fifth individual and eighth individual both are having more area in the wheel. So if you spin this wheel, right, if you rotate it, then finally what happens? There is a most probability that if you cover more area, there is a higher chance to get. If somebody covered, let's say 80%, so more chances that 80% will be picked out in the solution, right or not? So that is the concept of roulette hill. So what we are doing, we are calculating the cumulative probability in the case of roulette hill selection, because I told you if number of populations here we have considered 8. So after the process of selection also I want 8 different chromosomes, but these 8 chromosomes and these 8 chromosomes are not same. What I basically am going to do, I am going to replace some of the chromosomes with some other chromosomes that I tell you in this process. So we are calculating the cumulative probability. You can see here cumulative probability. So here we are calculating the cumulative probability in the column number B. So 0.0429 plus 0.0900. So if you sum these two together, you will get 0.1329. If you sum these three, you will get 0.266. Like that, here I am showing another one. We are getting 0.6388 here because we sum all this probability. So these are the probability which we have calculated earlier. This is the cumulative probability. Okay. Apart from that, relative selection says we have to calculate the expected count. So expected count is calculated based upon the probability and the number of populations. For example, probability we know, right? And we know expected count is 8. We multiply 0.0429 into 8. Similarly, 0.0900 is multiplied by 8. Similarly, here 0.1955 is also multiplied with 8. So you will get the column number A. Is it clear? Column number A and B. A is simply multiplying the probability with 8, B is nothing but we are calculating the cumulative probability, right? And what is C? C is nothing but C is generating a random number in the range of 0 to 1. Okay, any random number you can generate in the range of 0 to 1. Now, what is D column? D column says that, for example, you are generating 0.259. 0.259. So after generating a random number in the C column, you go to B column and find where 0.259 lies. So you can check whether the value is 0.0429. No, 0.259 is more in comparison to 0.0429. Similarly, 0.038, sorry, 0.259 is also more than 0.1329. It is more than this one, but less than 0.266. That's why we found that the range of getting the value is the population number 3. That's why I have written here the value is 3. So what actually doing, whatever probability you have generated, you compare with the cumulative probability. Where you will get immediate less than, that value you have to write here. So let us try with another value to clear our idea. So for example, 0.038. Now tell me 0.038 is less than 0.0429. Yes, it is true. So I have written here 1. Similarly, you determine the column D based upon the cumulative probability and whatever the value in the random number. Okay, once D generated, what E column says that? E column says that you have to count how many times 1 is repeated. In this column, how many times 1 is repeated? 1 is repeated once. How many times 2 is repeated? 2 is repeated once only. How many times 3 is repeated? Once only. How many times 4 is repeated? 4 is repeated one time here, one time here. That's why you can see fourth population corresponding E column is 2. Right? Fifth population case, also it is repeated twice. You can see here, right? So I'm writing here 2. Rest case it is 0. And eighth population case you are getting 1. So now you can see if you sum it also it is 8. That's why I told you before selection process also it is 8. After selection process also 8. Again, it is a different variants of genetic algorithm, right? I'm not saying it is the only followed. Many authors have taken 100 population, they shortlisted 10. But in this example case, they are taking 8 and they are generating 8. But whatever population they are generating here, that is not as same as this particular population. Why? Because they have discarded which population? They have discarded the population number 6 and population number 7. Because E column says that you have to discard these two. If you discard these two, you have to make a copy. Which one you will make a copy? Those count is 2. That's why you can see 0, 0, 1, 0 and 1, 0, 0, 0. It is repeated twice. And 0, 1, 1, 0, 0, 1, 0, 1, 0. It is also repeated twice. That's why whatever 8 populations you have given, you are not finding the same population, but the count is same. Is it clear how we are doing this thing?
So just to quickly repeat the process once. We are expecting a population count 8 to take the cumulative property of
Here we are calculating, madam, cumulative probability, right?
cumulative
Okay.
probability in B. Then take a random sample. From the random
Random
sample,
sample.
give the where the cumulative property lies, and we,
Right.
since it is a random sample,
Hmm.
the random sample has to have one of each, because
Yes.
this is in a very large population. So
Yes.
then we see something will replace. The probability has appeared to be. So this happens in each iteration.
This process you have, no, this process we are not doing repeatedly. It is done only once.
Okay, sir.
The selection process is only once, right? And whatever value you are getting here, and
Hmm.
based on that we are calculating the frequency here. Like 4
Okay.
is repeated twice means corresponding to the fourth we have to write 2. Fifth is
Hmm.
repeated twice means fifth column, sorry, fifth row and E column we will put 2.
But this is,
Okay.
the n will be very very large, right? Here we have taken just a
N
small
is very
number.
large. In any case, N is very large.
Okay, sir.
Just for an example, I have given it is a very small.
Yes, I
Okay.
got it.
Yeah. So this is the process. Whatever I have explained, you can go through the slide. I will not repeat. But there is two issues. Okay. One is called as population diversity. Another is called as selective pressure. Okay. What population diversity says? Population diversity means that the genes that are already discovered as good individuals are exploited. Okay, both case what we are doing, if a particular population is good, right, that we are only exploring, right? So many researchers also suggested that sometimes what happen, if a population is not good also, let the population suffer. So the next generation case, maybe the population will may perform a better choice, right? For example, let's say in the first generation case, let's say their parents are good. Second generation case, the children are not good. Okay. So third generation case, they will say that no, our parents have not done good work. That's why they are suffering. Let us do good work. So many works also suggested that not to take only good individuals. Sometimes you have to prefer those people who are not doing better also. That is also a variant of genetic algorithm, right? So selective pressure is focusing here that degree to which the better individuals are favored. So no doubt both are focusing on how we are going to get good individuals. So sometimes this type of solution leads to higher convergence rate or slow convergence rate, right? Always these higher convergence rate happens with respect to high selective pressure, or low selective pressure leads to slow convergence rate. So we have to find some kind of balance to solve this particular problem, which we faced in the case of rural till selection, right? If you favor the good individuals, like here you can see, if I favor these two individuals, they will cover more in the wheel. There is most probable chance that they are going to get the selection, right? So in order to avoid this one, we have another selection method that is called as tournament selection. Like we know football match, we know cricket match, and we know any match happens between two different two different parties. So what we are doing here, suppose I am taking 8 different individuals. Assume that their fitness value is this one, 2.10, 3.11, and so on. Okay, you have calculated fitness value based upon a fitness function. Assume that. So now I have randomly picked two different teams. Yes, sir. If you have any question, you can ask. Yeah, Farooq, sir.
Yeah, sir, I have a doubt in the previous slide in column D. How can you write instead of 2, you have written 3? In column D, in the population number 1 in column D, instead of 2, you have written 3 here.
This
I
one,
think,
sir.
yeah.
So 0.259, sir. 0.259 less than, we are checking if this value is less than this value or not, which is not true. Okay, this value is not also less than this one. And this value 0.259 is less than 0.266. So as we achieved here, that's why we are writing 3.
Okay, sir.
Okay.
Okay, sir. Done.
No, there is no specific condition. See, when you implement your research problem, you can decide what are the parameters you have to use. Don't follow whatever parameters I am discussing. You can make a variation. Variation makes better result. Don't follow all the things whatever given in any research paper. You apply your things, implement it. You may get a better solution than whatever solution exists in the literature. So what we are doing in tournament selection, as I said, there is 2 teams, right? For example, out of these 8 teams, I have randomly selected 2 teams. Let's say team number 2, team number 4. Okay. So I have looked into what is the fitness of 2 and what is the fitness of 4. And let's say our objective is to maximize. So which one is better? Obviously, team 4 is better. So team 4 count is 1. Okay, just like we have maintained a point table in cricket match. So here also we are maintaining a table. Okay, then 4 is the winner. So select string this one. So 4 is selected. Then there is a match between 3 and 8. Okay, if you go in 3 and 8, 3's fitness is 3.11, 8 value is 4.55. Who is the winner? Obviously 8 is having more value and it is a maximization problem. So that is better. So we are selecting 8 is the winner and selecting that particular string. Like that, we carried out several matches. Okay, you can say that there is also a fixed set of matches, right? Just like we are doing in cricket, right? Some fixed set of matches by taking different pools, so they will play the match. Okay, like here 1 and 3 also another match. So 1 and 3 case, if you go for 1 and 3, Sorry, I have written wrongly here. This is 5-1 and this is 5-3. So 3 is the winner and 1 is the loser, right? So out of these one, so we'll see who won the maximum match. Okay, that is going to be selected, and those teams which are not even winning a single match, we are going to discard it. So what we are doing here, you can see here, what we observed with this tournament selection, 2, 3, 5, 6, they are chosen only once, 4 and 8, they are chosen twice, and 1 and 7, they have not chosen single time also. So what we are going to do? 1 is going to be discarded, 7 is going to be discarded, and this 4 population is going to be duplicated, and 8th population is going to be duplicated. Okay, so this is the solution given in the tournament selection. So roulette hill case, if you remember in the previous case, 6th and 7th population we have omitted. But tournament selection case, it suggested that 1st and 7th solution you are going to omit it. Right? That's why you see there is a difference, right? Here we are saying 6th population you omit, whereas here we are keeping 6th population and we are omitting the 1st population. So
6 is weak, sir. See, 6 is as it is weak. It was chosen only once, sir.
which one, madam?
So 6 is weak even here. It was chosen only once.
Here, madam, in this case or roulette hill case?
In the tournament also 6 is still weak, sir.
6 is only once, right?
Yes, it is only once, but that means it is weak, not chosen twice.
No, 6 is not chosen, madam. Only 4 and 8 is chosen twice, madam.
Yes, sir.
4 is duplicated. That's why I make a error mark here. 4 is will repeat here. 8 will be repeated here. Now, what I try to tell you here, you can see with respect to the selection also, the process is different. So although both case 7 is coming, but there is a difference in 1 and 6. So sometimes what happen in your method case, roulette hill will not perform well, but tournament selection is going to work well, or vice versa may be also true, right? That's why different selection method people are applying to choose an optimal, choose a best selection method in their respective program. We cannot formalize that always tournament selection is better than the roulette hill selection.
Yes, sir.
Okay, and we know that in case of roulette hill selection, there is another issue which I already. Yeah, Naveen sir, please.
Sir, am I audible, sir?
Yeah, please, sir.
Yes, sir. But how can we judge that in order to make the balance between diversity and selective pressure, what we have to do? For example, right now, what you demonstrated here, for
Yes.
that tournament is better because it is balancing both. And
Yes.
that one, first one, roulette wheel is means offering first feature only, that is diversity. But
Yes.
in our problem, how can we judge that which one we should take for optimization
Good
purpose?
question, sir. But there is no standardized selection method or crossover or mutation. Till now, nobody will say that irrespective of problem, if you apply this type of technique, it will give better result. There is no answer for it. It is difficult to determine the best one. Just like somebody can say the roulette hill is not better, I'll go for, let's say, rank selection. Just I am going to tell you, because rank selection is a better in comparison to roulette hill. In that way, you can favor a particular selection method and you can omit another selection method. But there is no standard guidelines to find it.
Okay, sir. Thank you, sir. Thank you.
So see here, there is another selection method that is called as rank selection. So what I told you in roulette hill, if a particular population occupies, let's say, more space, in this case it is 75%, so it is difficult to do it, right? So every time that population is also going to come, okay, other population, they will not come, right, in the picture. So in order to avoid that, there is a rank selection. So what rank selection says, you have to rank each and every population starting from 1, 2, 3, 4, 5. But the population which is having more space, so here fifth population is having more space, so that will be given rank 5. Okay, if there are 5 population, then the highest area occupied by a particular population is given rank 5. Then you can see rank 4 is allotted to the 4th population. The next area is covered by most area covered by the 3rd population. So we have given rank 3. like that rank 2 and rank 1, right? Then what we are doing, we are calculating sum of the ranks. Sum of the rank is, it is 15, right? And we calculate the percentage. What is the percentage we will get here? 1 by 15, 2 by 15, 3 by 15, 4 by 15, and 5 by 15. So this much percentage we are going to allot to this roulette here. So in comparison to this particular one, this may be a fair solution, right? Although still also you can see the more area is occupied by that particular population only, but not like the previous one. That's why many people prefer this rank selection instead of taking the relative selection. Okay, so like that, there are other methods are there. I'm not telling you each and every method. There is another method also.
Sir, sorry.
Yeah.
Can you repeat once more that one, that final result? Okay. Means what we were doing in case of roulette wheel, approximately the similar approach we are following here also.
Yes.
But
in comparison to this one, here you can see population 5 occupies 75% of the space.
Yes, sir.
But in this case, it is occupying only 33% of the space. So what we did, we ranked them.
Yeah, yes.
Understood. 5 population, we rank them.
Yes, sir.
And we divide the current its rank divided by sum of all ranks.
Yes, sir.
So whatever value.
The rank is the weight, not the area now.
Yeah, weight. We can say weight only.
Rank is the weight, not the area. It is 5 times heavier than the first one, but not having 75% of the area. It is 5 times heavier than the first rank.
5 times
heavier, rank 1 to rank 5, and divide by total the summation of all ranks. So the weight has become one weight of the rank into 5 times the rank, but not taking it into consideration the area. So this method, I am not sure how best it could be applied, sir. I am not able to get an example for it.
But you can see, madam, in the previous case it is 75%. In this case it is 33%.
33%. I appreciate that, sir. But how do we apply this?
No, this is a particular step that you have to apply to any application.
Okay,
in any application case, you have to try and see that whether there is a variation in the result or not. To say that one is better than other selection method.
Okay, sir.
Or in other words, sir, sorry, sir. In other words, we can say that we are just relaxing the diversity to just approaches towards selective pressure in somewhat manner. Not maximally. In somewhat manner, we are trying to make a balance.
Yes. Correct.
Yes.
It is a kind of balance only. Correct.
Yes.
And whatever madam also said, that is correct, because we are taking sum of the rank is 15, right? So if we take 15 is 100%, then obviously 5 is 33%, right?
Yes.
So 1/3. So it is occupying 1/3 of that particular area. So in that way, it's also it is making a balance.
Yes.
Okay, like that, there are other methods are there. So I'll go to crossover. We have very limited time, and so crossover. The main challenge is that how to pick a particular population. For example, we have taken 8 different population in initial population. After applying the process of selection, again we have 8 population, right? So in our new population, we have 8 different population. So what you have to do in order to do crossover, you have to choose 2 different population. So how to choose these 2 population? You have to generate randomly. I'll tell you in subsequent lectures that how to generate random number using MATLAB if you don't know. So through that you can choose any 2 population. Okay. And once you choose 2 population, for example, let me call these are P1, P2 up to P8. So let's say I have selected P4 and P5. Okay, randomly it is coming 4 and 5. So I am taking this population, right? 4 and 5. Then I have to find a point where I will make a crossover. For example, I will choose, let's say, this particular point I want to make a crossover. So for example, like we have male chromosome, we have female chromosome, right? So child is having some behavior of the male parent as well as female parent, right? So we need a cross side point, right? Let's say cross side point is, let's say if it is a, I can say, let's say it is a, we represent it in a 8-bit. Then we have decided to make a crossover here, right? So for example, if you see here, A is represented as a 5-bit binary, B is represented as a 5-bit binary. So these two population is selected randomly, and we choose a cross-site point here. So if you generate two children, so first children is going to take this part of the A and 000 part of B. On the other hand, second child is going to take first two zeros of B and three ones of A. So that these two are called as the children. Okay, these are called as the parent. It may be parent number 4, it is maybe parent number 5. Now we have generated two children. Let's say C1 and C2. Okay, so crossover objective is to generate more population, right? But in our pool we have 8 population. We'll keep only 8 population only. We'll not increase the number of population. Now we'll check after mutation whether this population is previous population is better or the updated population is better. Updated population means the children population is better. If children population is better, then definitely we are going to replace the children with parent. Otherwise, we are going to keep only parent as it is. So there are different type of crossover we have. So like whatever I told you in the previous slide, that is called a single site crossover. So we have selected a particular point. We took the first part of parent 1 and second part of parent 2, and we took first part of parent 1 and second parent 2 and second part of parent 1. So we generated two different children. So always you remember, crossover is applied to the parent and mutation is not applied to the parent, mutation is applied to these children. Okay. So, but other type of crossovers are there. Slowly I'll tell you. So there is a 2-point crossover. So 2-point crossover case, you will choose two different points. Let's say one cross-site point you are getting here, another cross-site point you are getting here, right? What you will do? You will take first part of parent 1, second part of parent 2, third part of parent 1. Similarly, first part of parent 2, second part of parent 1, and third part of parent. So that will be generated in your children. Similarly, we have multi-point crossover also. Single point crossover we have seen, but 2-point crossover we have seen. Multi-point crossover case, what we are doing? There is two type of multi-point crossover. You can go for even number cross sites, or you can go for odd number cross sites. So for example, if I take a ring, okay, for example, you can see this is just like look like a ring. Ring case, there is no beginning and no end. Okay, so there is a ring like this, there is another ring like this. So what you can do, randomly you will choose one part here, let's say another part here. One children, another part you can choose by taking this part and this part, that is another children. Okay, but if you go for without a ring, if you go for a straight line kind of thing, right? There you can choose cross site point 1, cross site point 2, cross site point 3, or cross site point 4, and so on. So in that case, what you will choose? You will choose parent 1, parent 2, parent 1, parent 2 alternatively to generate child 1. Similarly, you can choose parent 2, parent 1, parent 2, parent 1 alternatively to choose another child, to generate another child. So again, there is a challenging problem like previously what I told you. In selection case, it is difficult to determine which point of crossover is better for your case. Again, it is a hit and tail methods, right? We cannot say that which particular crossover is going to be suitable for a particular problem. So there is another crossover that is called as uniform crossover. Okay, here what happened? Each bit from either parent is selected with a probability 0.5. So if I take two different parent, so I'll toss a coin. Okay, probability is 0.5, right? Toss, if I head is it is 0.5, tail it is 0.5. So for example, if it is head, then I am taking from parent 1. If it is tail, then I am taking from parent 2. That also I can do. So let's say these are the interchange positions where what we are doing, we are taking parent 1 usually. If there is an interchange, then we are taking parent 2. Here there is no interchange, I am taking parent 1. Here there is an interchange, I am taking parent 2. Here there is no interchange, I am taking parent 1. Here there is an interchange. I am taking parent 2. So in this way, I can generate the child 1, and rest part will be becomes the child. So you can go for any number of crossover, any types of crossover which comes to your mind. Just our objective is to generate 2 different children by taking 2 different parents. Okay, there is a uniform crossover by taking crossover mask. Previously, I told you interchange, but here there is a crossover mask. What do we do crossover mask? Crossover mask is if the value is 1, then you will take from the first parent. You can see it is 1 means I am taking offspring is taking the things from parent 1. But if it is 0, crossover mask is 0, so it is taking from parent 2. Like that also you can do crossover. Okay. And once you generate offspring 1, just the reverse of that, that will be your offspring 2, right? So you can do uniform crossover with interchange, or you can do uniform crossover with a crossover mask. Crossover mask will guide you whether to choose a parent 1 or to choose a parent 2. Okay. So next point of
Sir,
crossover. Yeah,
so
madam.
where in what text will I find it properly laid down? All these crossovers, textbook, sir.
I'll give you, madam, reference. I have given a book. In fact, this slide I have prepared based upon my knowledge as well as from one book that I'll tell you.
So you, but now the levels now are becoming very complex, and it makes a lot of sense when to use this. But the examples have to be of that nature.
Sir, if it is possible, then if you could share this slide even also in our WhatsApp group, it would be better for us.
Slide is already shared in the WhatsApp group.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes.
You go
Thank
to
you, sir.
yeah. You go to materials, you will find the slide. No problem. Okay, there is another crossover that is called matrix crossover. Okay. So for example, if you look into image processing kind of application, in image processing type of classification, we represent a image in the form of pixels, right? So there also we can do crossover. For example, there is a 256 cross 256 image, right? So I am taking 2 different, let's say, image, and I am making a fusion, or I want to do crossover. There also I can do. So some part of the parent 1 will come, some part of the parent 2 is going to come. Okay. So there are a number of ways we can do the process of crossover. So next important part is what is crossover rate. So crossover rate is nothing but number of pairs to be crossed divided by the fixed population, right? Generally, crossover rate is suggested in between 0.5 to 1. Okay. So suppose you have taken a population size of, let's say, 200, as it is suggested that population size of 30 to 200, it is 0.5 to 1. So fixed population is 200. So if you want to do crossover, you can do 100 crossovers to 200 crossovers per iteration. Per iterations. Like here we did crossover with respect to 2 parent. Similarly, you can choose another 2 parent, perform the crossover, choose another 2 parent, again do the crossover. Like that, maximum number of crossover you can do with a 200 population, 30 to 200 population. If I take 200, then it is 100 to 200. So that ratio is 0.5 to 1. So if it is applicable to our 8 population case, so how many crossovers we can do per iteration? Can anybody say if it is applicable to?
4 to 8, sir.
Yes, it is 4 to 8. The minimum number of crossover you have to do is 50%. Okay, but you have to choose again. Don't go for random value, but every paper in the simulation result you will find what is the crossover rate. The meaning of crossover rate is that many number of crossovers, that many percentage of crossover is done per iteration. And I assume that there are 20 iterations means 20 times they are repeating the same. Okay.
So is it because then I can see some other behavioral patterns coming out in the population? That is why 0.5 to 1.
Yes, madam. What actually we want to do? We actually these are not the children. Crossover is not the end of the process. After doing mutation only, whatever you are saying behavioral pattern that you can find. It is a process to find the behavioral pattern, but behavioral pattern is not found in the in after the crossover step.
Crossover. Okay, sir. Got it. Thank you.
Okay. So now there are some other methods are there, like inversion case. Inversion case, what I can do, just like a 2-point crossover, right? I am selecting 2 different points and I am doing flipping of bits. If bit is 1, I am changing it to 0. If the bit is 0, I am changing it to 1. That way also I can do, right? I can choose 2 different points, 2 random point, and in between that point, I can invert it. That also I can do. There is another process called as deletion. That's why I told you there are several inheritance operators are there, but the most popular operators nowadays we are using, that is crossover and mutation. But these operators are there from long back. See here, deletion. What deletion says that again you will choose some range, right? Let's say in this population, any 2 or 3 bits at random you have to choose, and you select it and you repeat the one. For example, I am choosing these are my cross-site point. Okay, and 50% of the values I am keeping as it is, and 50% of the value I am discarding, and I am making copy of this 50% bit. So that is called as deletion and regeneration sometimes. Okay, we deleted it and we have copied it. Or you can go for complete regeneration also, right? Without copying. Here we are regenerating just by copying, right? Sometimes what you can do, you can make 2 points and totally you have to delete it and you have to regenerate it. That way also you can do. Like here you can see I have completely deleted it and I have generated again a set of bits. That also can be possible in the case of crossover. Okay, there is another one is called as segregation. It looks like our 1-point crossover, right? What we are doing here, parent 1 is there, parent 2 is there. Let's say this is my cross-site point. What I'll do, I'll take the first part and second part of parent 2, and on the other hand, I'll take second part of parent 2 is and first part of parent 2. Just like single point of crossover is we are separating this one, so we call that as a segregation. But it behaves same as our 1-point crossover. Okay, there is another one that is called as crossover and inversion. So you will perform crossover first, then you have to invert it. So take 2 population. So this is first population, this is second population. So what I will do, first is 2 random sites are chosen. 2 random site means this is our first site, this is our second site, and we have to exchange between 2 mates. Exchange means this particular part will go to your child number 2. Okay, this is parent 1, this is parent 2, and this particular part which is parent 2, that will go to child number 1, right? Just like a 2-point crossover. Then once crossover is done, what I'll do over the process of inversion. Inversion means this 1100 is going to be flipped to 0011, 0110 is going to be flipped to 100. What do? We simply do here 2-point crossover followed by inversion. So we call this one as a crossover and inversion. But the problem with crossover, if you identify till now, for example, if you have a sample 0001, another sample is, let's say, 0100. Is it possible to do any kind of crossover to get a 1 bit here? Is it possible to apply any kind of crossover except regeneration? I told you one thing, regeneration, in which you are generating a new number, right? You do any kind of crossover, it is not possible to get this bit is 1. Or you do any type of crossover, you will never get this bit is 1. That's why there is a need of mutation. So mutation, what we are doing, we are picking a particular bit and we are changing that particular bit. We may change the bit with the same value, or we may change the bit with a different value. So see one example here. Like I am taking 4 population. In 4 population case, all the first bit is 1. So all 4 strings have 0 in the leftmost bit position. So it is not possible to flip this particular bit by using any kind of crossover except regeneration. Regeneration case, we are generating a new value. So new value may be 1. Okay, in next iteration, it will help us to making it 1. So that is possible. So the solution is that we have to go for the process of mutation. For example, in a particular population, I have selected this particular bit, which is earlier 0, and I have flipped that particular bit. So 0 is now changed to 1, right? Similarly, if you go for a real number, so real number is, let's say, minus 69.4. So I have flipped it to another value, that is minus 67.5. I have generated another value, 67.5. So which we cannot do in the case of crossover, that we are doing in the process of mutation. So with a population of 30 to 200, I told you crossover rate is 0.5 to 1. But what is the mutation rate here? 0.001 to 0.5. So with a 200 population, maximum number of mutation you can do is 100. But minimum number of crossover you have to do, this is mutation. If you go for crossover, minimum number of crossover you have to do is 100. So this is also you can get in experimental result. Those who have applied genetic algorithm, in their case you can get mutation value is number of mutations they are doing at max 100, or number of crossover they are in 100. So they are mentioning crossover rate and as well as the mutation rate. So many people have applied one's complement also, because one complement can help you to flip. For example, I want to flip this bit. What I can do? I can simply flip that bit 0 to 1. So that is also can be treated as a mutation. Some people applied bitwise AND. What we are doing in bitwise AND? In this case, if both bit is true, then only the output is true. If one of them is false, like you can see 0, 1, 0 means false. 1, 0 case 0 is false. 0, 0 case both is false. Then the output is also false. In the case of bitwise AND. But when you go for bitwise OR case, what we are doing? Bitwise OR case, one of them is true. In this case, both is true. In this case, one of them is true. Then the output is true. Sorry, this is bitwise exclusive OR. In exclusive OR case, in 1, 1 case and 0, 0 case, you will get the value is 0. And if there is an alternate bit, just like 0, 1 or 1, 0, in that case, you will get the value is 1. So you can see here, this is 0, 1, just changing a bit in both parents. So output is 1. 1, 0 case also it is 1. But if both bits are same, then the output is 0. Here also both bits are same, that's why output is 0. So these operators also can be applied for doing mutation. Similarly, we have bitwise OR, we have left shift operator, we have right shift operator. Left shift, we make a shift towards left up to, let's say, 2 digit or 3 digit based upon this input value. So for example, in this case, you can see 0 is shifted here, 1 is shifted here, and 1 is shifted here, 0 is shifted here, 0 is shifted, 1 is shifted here. So this 1, 0 is going to be discarded, and you can regenerate these two by bit. Okay, you can put 0 or 1, you can regenerate it. So this type of operators can also be used if there is a sequence of zeros to make it 1. Okay, so I am telling you an application, whatever we have studied till now. Let us summarize that one with this example. So let's say our objective function is count the number of ones. Okay, and I am taking, let's say, 4 different populations. Okay, for a small example, I am taking 4 number populations. So how many ones are there here? There is 3 ones. Out of the maximum number of 1 is 10. So fitness is 0.3. In this case, how many ones are there? 5, 2, 7, 2, 9. So 9 by 10, you are getting 0.9. Okay. Now, what is the average fitness? Average fitness is 0.6, right? So if I calculate fitness divided by fitness average, so I am getting 0.5, 1, 1, and 1.5. This is relative, right? Earlier also we have seen why we are calculating average to find the relative one. So what it says that if a value is higher, it is a maximization problem. So that will be repeated twice. These two value will repeated one time, and this one we are going to discard. So there is a theory which we call as Darwinian theory of survival, which says that strongest individual should have 2 copy. This is strongest individual, so it has 2 copy. So it is going to replace the first one. Average individual should have 1 copy, and those individuals which are weak, so they will die. So don't take any its copy, right? So now, if you go for, let's say, this I told you, right? So what we are going to do, we are going to discard this one, right? The first population, and as the last population is better, so I am going to just make a copy, right? So now the second population is written in first, I think third population is written in second, and fourth population is repeated twice, right? Now you have applied the process of selection, you have removed something, then new population came. What is the next process? We have to go for crossover. So as there are 4 population, how many crossovers we can do? Minimum number of crossovers we have to do is 50%, right? So 2 crossovers we have to do. And in this example, it may not be, right? Because it is a small example. So crossover we are doing, so we have decided that this particular population is going to crossover with population number 1, and first population is making crossover with 4. So obviously 1 to 4 means it is 4 to 1. At what point they will do crossover? The cross side point is 1 and cross side point is 5. So we'll take these 2 population and make it a crossover. So you can see here, I am taking the first part of first population, then let's say I am taking this particular part, okay, second part of second population, then rest part of the first population, and remaining will be another population. That means children 1 and children 2, right? So if you do this one, you will get this one. Now, if you look into fitness, although we are not calculating fitness after the crossover point, just for an simple example I am showing you, you can see the fitness is now improved to all ones. Okay, all ones means 10 out of 10. So we are getting 1, right? All values are equal to 1. So we are getting best fitness here by making a particular crossover. But we have to perform the mutation. The mutation means what? I have to choose some points. Let's say I am choosing 6th bit of the string 2 and 1st bit of string 1. So these values will be decided based upon the random number generation. So what I'll do, I'll make change in these 2 bit. So I'll choose this bit, I'll just flip it. Okay, 1 is going to be replaced with 0 and 0 is going to be replaced with 1. Okay, so 2 out of 40s are muted, so the probability is 0.05. In the previous case, let's say we are taking 2 pair, 1 with 4 and 2 with 3. Okay, so it is 50%. But anyhow, 2-3 case, assume that let's say there is no change. After making the crossover, it is made in such a manner that there is no change. That also can happen. Sometimes crossover is not beneficial also, right? So now what we are doing, so crossover we have done twice, that is 50%. So you can go up to 100%. Mutation we have done only in the 2 bit out of 40 bits, okay, and you can go up to 50%. So you can see after doing this particular process, you got 2 children. I can write that is a modified children 1, modified children 2. Parent 1 is there, parent 2 is there. After mutation and crossover, after crossover and mutation, we got modified children 1 and modified children 2. So I will check the fitness of modified children 1, modified children of 2 and compare with the P1, P2 respectively. So if P1 is better, then I am going to discard modified children 1. Let's say modified children is 2 is better, so I am going to discard my P2 and I update my population in the mating pool. So this will help me to go for the next iteration. Okay, this process I will do with doing the next iteration. Like that, this process will be repeated unless my termination condition is satisfied. Okay. So this is the whole what I told you. So we never check fitness of the children. We check the fitness of what? Modified children. So that is the important thing which I am highlighting. Okay. So after crossover, you are getting children 1, children 2. Then after mutation, you are getting modified children 1, modified children 2. If they are unfit children, discard it. If they are fit children, you have to add into the new population. Okay. But many research articles also suggested that even if they are unfit children, you add into new population, so that in next iteration you may get a better value.
Sir, the fit children are added, but parents are removed.
Parents are replaced.
Replaced.
Yes. Yeah, removed or replaced too. Both are same. So at any point of time, new population is same only. We are not adding any population. We are not updating. We are only updating the population. We are not adding or we are not removing also. 8 population is 8 irrespective of the number of iterations. So these are the references you can go through. Okay, that is also some pointing to several research articles also. And you told about books, so I suggest you to go through this book, Neural Network, Fuzzy Logic and Genetic Algorithm, Synthesis and Application by Professor Vijay Lakshmi. That is a good book to study all the optimization algorithm and neural network.